Momentum is the fourth major topic in physics after kinematics, forces, and work and energy. In this video, we will introduce the concept and look into several examples. Momentum is symbolized with the letter P. It is defined as the mass of an object times its velocity. Since velocity is a vector, momentum is also a vector. Mathematically, it's not hard to solve, but it gives rise to one of the most important rules in physics, the law of conservation of momentum. Just like energy, momentum is a conserved quantity. You cannot create or destroy momentum. You can only redistribute it between objects. Suppose you have a collection of objects. Such a collection is called a system. The law of conservation of momentum says that when two objects in the system collide, their total momentum before the collision equals the total momentum after the collision. Let's apply this. Here, we have a 2 kilogram red block moving at 5 meters per second and a 3 kilogram blue block standing still. We see them collide and stick, and then they move off together. This type of collision, in which the objects stick together, is called an inelastic collision. We will define inelastic collisions more strictly later on. For now, we will analyze this collision. We have to set up an equation that represents the momenta before and the momenta after the collision. We will label the momenta of the two objects as P1 and P2, P1 standing for the red block, P2 standing for the stationary blue block. Thus, P1 plus P2 before the collision equals P1 plus P2 after the collision. This is a mathematical expression of the law of conservation of momentum. Let's expand these terms. Since P is equal to mv, we can expand all of these terms to yield m1v1 plus m2v2 before the collision equals m1v1 plus m2v2 after the collision. Since the objects stick together, v1 after the collision equals v2 after the collision. So we can replace those terms with a single v final and factor that out. Then we substitute for all of the known information. With a little bit of math, we find that the final velocity is 2 meters per second after they have stuck together. Now, let's do a variant. Suppose the 2 kilogram object had been moving the same way as before, but the 3 kilogram object had been moving leftwards at 4 meters per second. Again, they stick together in an inelastic collision. What would the final velocity be? The setup is the same as before, except that the initial velocity of the 3 kilogram object is now negative 4 meters per second. After that, we do some math, and we find that once the two objects collide and stick, they will end up moving leftwards at 0.4 meters per second. That's negative 0.4 meters per second. Next, a slightly more complex variant. Suppose the 2 kilogram object had been moving the same as before, but the 3 kilogram object had been moving upwards at 4 meters per second. That is 4j meters per second. Again, they stick together in an inelastic collision and fly off at an oblique angle. What would their final velocity be? When multiple axes are concerned, we have to treat the I and the j components separately. That would be a little bit like treating the x and y components separately in kinematics or in forces. When we do the math out, we find that when the two objects collide and stick, the combination will move away with a velocity vector of 2 plus 2.4j meters per second. Or, if you prefer to see this in polar, that's 3.12 meters per second at an angle of 50 degrees. The opposite of an inelastic collision is an explosion. Explosions sound more exciting than they really are. It simply means that a single object breaks into two objects that then move away from each other. when the objects move away, momentum must be conserved. For instance, suppose you have a mass of 75 kilograms and you're standing on a skateboard. You're holding a 5 kilogram ball and you throw it at a velocity of 20 meters per second leftwards. That's negative 20 meters per second, I. You can probably guess that you will start to move backwards, but at what speed? Set up the law of conservation of momentum as before and then expand. In this case, we will treat P1 to be the momentum of the ball and P2 to be the momentum of you throwing it. We then break it down in the same way as before. M1 V1 before plus M2 V2 before equals M1 V1 after plus M2 V2 after. Initially, there's no motion, so the velocity of both you and the ball before the explosion are 0. After the explosion, the ball is moving at negative 20 I meters per second. The only unknown is your velocity, and with a bit of math, we get a velocity of 1.33 I meters per second. You might notice that when the character threw the ball, he recoiled. This is exactly in line with Newton's third law. Conservation of momentum and Newton's third law are very closely connected. One last definition is useful, the definition of impulse. Remember that conservation of momentum says that momentum is conserved within the system. But what happens if something feels a force from outside the system? For instance, let's say that this billiard ball is inside the system, but the cue which is striking it is outside. In this case, we say the billiard ball feels an impulse. An impulse is a change in momentum caused by a force from outside the system. Impulse is equal to the change in momentum, that is, final momentum minus initial momentum. It is also equal to the force acting on the object multiplied by the time that the force operates. This has been an introduction to the basic concepts and problem-solving techniques in momentum. Next time, we will look at more advanced problems.